So like Ross said, I'll be talking about Nobrainer and applications of deep learning in neuroimaging. So deep learning is all around us. Deep learning is used in a lot of technologies that we interact with. It's used in self-driving cars so that the cars can understand the environment around them. It's used in chatbots. Facebook has really powerful face recognition in a deep neural network that they call deep face. Zoom is able to transcribe the audio from recorded meetings into text. And I haven't confirmed this, but I'm 90% sure that they're using deep learning for that. Google Translate is a great tool in part because of deep learning. And assistants like Amazon Alexa, Google Home, Siri, they all use deep learning to be able to understand our speech. And healthcare nowadays is becoming more interested in applying deep learning into its own practice. So this is a photo of me in the middle, and even this photo used deep learning. So this was taken using Apple's portrait mode. So this was with a single lens camera, and they used deep learning to create a depth map and then blur the background. So deep learning is really all around us. Let's see. Oh, and I wanted to actually connect this to Professor Richard's talk. If you notice, this is all part of the AI set that he was talking about. These are all tasks that humans do quite well, I would say. So deep learning is particularly well suited for imaging. And there are three main types of problems you can tackle in imaging with deep learning. So one is classification. This is taking some input and mapping it to some class. So for example, with the dog on the right side, classification might be, what breed is this dog? Or what is this an image of? Another problem is segmentation. And this is classifying every single pixel. So this question might be fill in the space occupied by the dog, or fill in the space of the dog's nose. And you can also, there's a third class that would be regression. And that's when you're mapping the features to some continuous variable. So for example, how much does the dog weigh, or how old is the dog? These are all continuous things. And a lot of us are familiar with deep learning now, at least the term, and its popularity really exploded back in 2011. And this was mostly due to improvements in hardware and the availability of data. As Professor Richard said, these models take lots of data to train. But the theory for these things has been around since the mid-20th century. So deep learning and neuroimaging, there are lots of places for deep learning in neuroimaging. One is brain extraction, which you see on the top left. That's a segmentation problem, figuring where the brain is in space. On the right is parcellation or segmentation of the brain, another problem that you might solve with deep learning. Even something like registration, which is aligning a brain to some template. And to do this, there are an abundance of frameworks. There's TensorFlow, Keras, PyTorch, MixNet, CNTK, Chainer, and probably many more. And probably someone's working on a new one right now. And a lot of them have great built-in support for working with 2D images because it's such a common problem, especially in industry. But I haven't seen one with great built-in support for 3D images like we have in brain imaging. So this is where Nobrainer comes in. This is a project, open source project on GitHub. And it's a framework for developing neural network models for 3D image processing. And it provides methods to convert data to deep learning framework friendly formats. It provides data augmentation methods, which can make your models more generalizable and perhaps less prone to overfitting. It implements several architectures, loss functions, and metrics from the literature. And it has a gallery of examples for processing data and training models. And I think one of the really special features about Nobrainer is that we include fully trained models for 3D segmentation. And we're trying to produce more models as time goes on. And I think this is really special because lots of pre-trained models exist for 2D problems like segmentation and classification. But I really haven't seen any for 3D segmentation. And it's built on top of TensorFlow and Keras. So we can use all of the cool features that TensorFlow affords, and also the ease of the Keras API. So this is one of the models that we distribute with Nobrainer. This is actually a special network in that it's a Bayesian network. So I won't really get into that, but what I will say is that in the middle you have the predictions from the model, and this is used to create a segmentation of the brain, similar to FreeSurfer's ReconAll, and it's more accurately a subset of FreeSurfer's ReconAll. So the reference values are in the FreeSurfer column, and the inputs are the structural scans. And you can see that the predictions are quite similar to the FreeSurfer scans. But the major advantage here is that the predictions take on the order of seconds if you have a GPU. And if you have a CPU only, then it's on the order of minutes, maybe 5 minutes. Whereas FreeSurfer takes several hours to do the same thing. Of course, ReconAll does much more than just segmentation, but I think the point still stands. So this is on GitHub. It was trained on over 20,000 brains by our collaborators at the National Institute for Mental Health, and it was published recently. So you can go online for the manuscript. And we also, I think you guys learned about containerization. Might be a new term to many of you, but we distribute a Docker container and a Singularity container so that you can use this on your own data. But just keep in mind that it is experimental. Another model that we distribute is a brain extraction model. So this is another segmentation model that's finding the brain in space. And the inputs here, these are two different scans. The rows are two different scans. The inputs are the T1 weighted images. And you can see that the model prediction overlaps quite well with the FreeSurfer brain mask. If you look on the bottom row, the scan had some motion. And you can see that because the brain has these striations. It looks a bit more like an onion. And it doesn't actually look like that. That's a motion artifact. So FreeSurfer, for some reason, failed on this segmentation. It missed a lot of the brain, but the model did decently well. It overshot a little bit, and it was a bit conservative in other areas, but it did decently. And so we also, have this model online. This was trained on 10,000 T1 weighted scans. And towards the end of Professor Richard's talk, he talked about transfer learning, starting off with, I guess, other data or like a pre-trained model. This model might be a great starting point for transfer learning. And 10,000 brain scans, I think even, that might not even be enough to have like a truly generalizable model, but I also think it's a great start. So another model that we use or that we distribute is a model that labels brain tumors, in this case meningiomas, which are the most common non-malignant neoplasm in the brain. Here we have T1 weighted contrast enhanced images, an expert label, and the expert in this case was a radiologist or a neurosurgeon. And then on the right, we have the model's prediction. And you can see that the model does quite well. And it even has a smoother prediction than the expert label. And this scan is the same person's scan, both rows. It's just that they have two tumors. And you can see that the model is able to detect both tumors. And so this model is also online under the NeuroNets namespace. This used transfer learning, actually, from that brain extraction model that I showed you. And so this, I think, is a great example of the power and utility of transfer learning, because here we didn't have that many samples. We had maybe 500 or 600 MRIs, and we were still able to produce, I think, great outputs. And we're in the process of publishing this model now. And I don't know if Professor Richards talked about specific architectures, but the brain extraction model and the meningioma model are 3D units. This is a common model. This came out in 2016. And that first segmentation network that I showed you, that is based on MeshNet. So, you might be wondering, how can I do this? I've seen a lot about deep learning, the power, the drawbacks. How can I actually get down into it? So there's, a pretty standard workflow that at least I follow. I would say that most people would follow this. Step 0, consider whether deep learning is the right tool for the job. This is very important. Deep learning is definitely not always the right tool, but when it is, it can be very powerful. So then step 1, get data. You need to have, this is typically a supervised process, so you need to have features and you need to have the corresponding labels, the reference. Then you create some processing pipeline where you standardize your data, maybe you augment your data. Basically, that's where you sort of manipulate your features and maybe your labels. You choose a loss function, which is the objective that your model is trying to minimize over time. Then you can choose a model. So there are lots of different architectures, and you have to implement it, or at least find some implementation online. And a good heuristic for choosing a model, I think, is to look at the various segmentation or classification, whatever problem you're working on. Look at competitions that happened recently in those fields and see what models worked well. Then you train the model on some data, you evaluate the model on other data, and then you repeat that process over and over again until you have something good. So, this is the end of the slideshow. I'd like to thank several people, particularly Satra Ghosh, who was my PI at MIT, the Gabrielli Lab at MIT, our collaborators at the National Institute for Mental Health. They taught me a lot about deep learning. Our collaborators at Brigham and Women's Hospital, and all of those who contributed to Nobrainer, and also Stony Brook University School of Medicine for having me now. And also thank you, BrainHack School, for the opportunity to share my work with all of you. I have the links here to the Colab and Bind notebook. Ross, I got those from the email that you sent to me. Hopefully they're the same.
So we have a couple of questions. I don't know, Ross, if you're monitoring the questions, but maybe that's a good time for having any question on the introduction to your practical.
Yeah, I'd love to take some questions now, absolutely.
Right, so one of them is, the last one I see is, what about segmentation for brain with, what was that, sorry?
Resections, I'm guessing.
Resection. Oh yeah, resection, yeah. Free software SPM usually cannot handle these since they are designed for normal brains.
Yeah, no, that's a great question. And actually, this is something that I ran into problems with the meningioma model, because sometimes the tumors were very close to the edges of the brain. And so brain extraction just simply wouldn't work. I don't think I have a good answer. What I will say, though, is that these models don't typically generalize well. So they will be good at the task that they were trained for, but they won't magically be good on data that they just have not seen. So if you train on brains that have no resections, and then you predict on brains with resections, I predict that it won't work well. So either you'll have to augment or you have to find brains with resections.
Thank you for that. And we have another question. Is the input data manually quality controlled for segmentation accuracy?
Another good question. So it depends on the amount of data I think that you have. So in the meningioma case, yes, every single scan was quality controlled. And actually they were quality controlled several times throughout, the process. With the free surfer predictions, we couldn't manually quality control all of them because in the smaller model we had 10,000 brains. In the larger model we had over 20,000 brains. So manually, no, we did not. But I believe our collaborators at NIMH had some sort of programmatic way to sort of do at least like a cursory quality control. And actually, there's some research going on now in using deep nets for quality control of brains as well. So, that's just another output for this. So the answer to your question is sometimes.
Thank you. And I think that's those are the two questions that are at least prominent in the chat. Okay. So maybe that's a good time to go on with the practicals. Would be like another layer.
Yeah, excellent. Okay, let's do it. So I'll open the Colab notebook. I should have opened this earlier. I'm sorry, but okay. But it seems to be running. So can people see my notebook right now?
Yes.
Okay. Should I wait at all for people to open this up?
Hopefully people have opened it up. We posted the links in the chat earlier. And so if anyone hasn't opened it up, or if anyone's having trouble getting the Colab or binder to run, please do let us know in the chat, and we'll kind of take those. So I think, Jacob, you can just kind of run through as you'd like.
Okay, excellent. So the first thing, for those on Colab, only for those people on Colab, we want to use a GPU. So in runtime, change runtime type, and then we're going to select a GPU hardware accelerator and save. Don't select TPU because I have not tested the code on TPU. So select GPU, please. Okay, and save. And so now we have access to a GPU. So this will basically like accelerate all of our model functions. Okay, so let's get started. So this notebook will have lots of breadth and some depth. So my goal here is to expose you to lots of different concepts and I guess give you pointers of where you can find more information, but to give you, some solid foundation at least. And, if you ever come across any issues or ways to improve Nobrainer, please do submit an issue or pull request. We really appreciate when people give us feedback on this. And Nobrainer has example notebooks on his GitHub. This notebook is different in that I tailored it more to the BrainHack and combined a lot of different concepts into one notebook. Okay, so we will learn how to visualize MRI prior to model training. So I think this goes back to the question of manual quality control. It's very important to at least understand the data that you're dealing with. Visualize your features, visualize your labels. And 2, we'll learn how to process features for model training. 3, we will be training a brain extraction model, a very simple one. We'll use a pre-trained Nobrainer model for brain extraction. and another Nobrainer model for multi-class segmentation. And those are two of the models that I described in the slides. And then we'll understand parts of a real world deep learning workflow. So, what one would do if they have access to lots of data and wanted to train a model. And so finally, we'll use Nobrainer to construct that workflow and train a brain extraction model using transfer learning.
Sorry, Jakub, I have a private question. Like, if someone hasn't seen where to put the CPU, GPU thing, can you just show that?
Yeah, of course. So if you're on Colab, so this does not apply to people on Binder. This is only for Colab folks. So go to runtime, change runtime type, and then select the GPU hardware accelerator. And for those on Binder, you won't have a GPU, but that's totally fine. I'll let you know the parts that do require, well, not really require a GPU, just go much faster with a GPU. And I included the outputs from those cells so that you can see what happened anyway. Okay, and I explained that here. Some wisdom, some bits of wisdom, garbage in, garbage out. So your model will only be as good as your data that you train it on. So, you can't just create like a magically amazing model if you don't have good data. Deep learning is not a hammer. It is not always the right tool for the job. I think that point has been hammered into you guys. And yes, a hammer is always the right tool for the job. Also, be patient. So this is a pretty steep learning curve, especially in BrainHack. I saw, earlier in the week, I looked at the schedule, you guys were learning about Bash and other things, and now you're going on to deep learning. So I couldn't really imagine a steeper learning curve. So kudos to all of you. And also be collaborative. That's really important in the open source community. If you find ways to improve Nobrainer, please submit an issue or a pull request, so that you can let us know. This is just some info about Google Colab and Jupyter Notebook. So now it's time to begin. First, we'll need to install Nobrainer. So please run this command here, the pip install command. This will install TensorFlow and Nobrainer, and you'll see that it's using the GitHub URL because I want everyone to use the same exact commit of Nobrainer. And here, the first time you run this, you're going to get a message that says this notebook was not authored by Google. It was not. It was authored by me, and I'll tell you that it's safe to run. So run anyway. And TensorFlow is already installed in the notebook. Oh, sorry. Excuse me. Put an exclamation point before that, so it's running like a shell command. Okay, and you'll see that TensorFlow is already installed and all those requirements are already installed. So it's just installing Nobrainer. And this is the command again. So I'll keep going, but to the TAs and the people helping out with this, let me know if people in the chat say I'm going too fast or too slow or anything. So now we import Nobrainer, and hopefully that works. Excellent, that works. So step one complete. We installed Nobrainer and we imported it. That is awesome. So Nobrainer is a Python package, and it has several different modules within it. I won't go through all of these, but I tried to basically separate out functionality in a logical way. We'll be using functionality in the models module, TF records. Actually, we'll be covering a bunch of these. So let's move on. So the first step is to get some data. So Nobrainer includes a function to download some test data. And this comes from this data set here, I guess from NIH, but it's packaged by DataLad.
Can we have a quick raise of hand for all those people who went up to the import Nobrainer, just making sure that people are on board? So
how do we run the first command? Isabel, okay. I'm sorry I didn't explain that better. So this is how you do it. So I should have included this. This was a bit of an afterthought, I think, for me. So copy and paste this Python install command. And then if you hover over here, you'll get a button that says add a code cell, and then add an exclamation point, which basically runs this as like a shell command instead of a Python command. Copy it, and then run that cell. And that will execute that as if it was running in bash because of the exclamation point. Is anyone having trouble with that bit? Yes, the exclamation part is important, yes. Yeah, in Jupyter Notebook, you can, if you use the exclamation mark, then it's going to run that command as if it were a bash command. Module not found. Did you install? Oh yeah, which module? Yes. Okay. Kat, did you install using that Python pip install command? Or Kat, sorry.
So I think what may happen is that those commands all need to be prefixed by exclamation mark. I'm not sure everyone has seen that fully.
Yeah.
And the reason is that this is a Python notebook, so the kernel is in Python, and you want to this exclamation mark is telling the kernel, say, hey, use bash for running those commands.
Yes, of course. Okay, so I'll show how to run the command once more. I really should have included this inside the notebook. I'm very sorry, but I promise this is the only place where you'll have to add a code cell. So, first, there are two ways. So first, if you hover between two cells, you'll see you can add a code cell. So I'm moving my mouse. You can add a code cell. And then you need to copy and paste that command, that Python pip install command here, but you need to preface it with an exclamation mark, which means run it in bash. Okay.
And we have seen all those pip install commands during the week, so I think it's a nice little exercise and making sure that this is you master those little steps that are critically important. Maybe Jakub, you could tell us, where is this command running?
So if I understand your question correctly, this command is not running on your own computer. It's not running in your browser per se. This is running on someone else's server, basically. In the case of Colab, I guess it's Google's servers. And JB, if you want to correct me or add to that, please do so. In the case of Binder, I guess, I don't know whose servers those are, but they might be donated or something. I'm not sure. But basically, it's someone else's servers, so you don't have to install these things yourself.
Right, exactly. And in case of Binder, this is like some of Berkeley resources. Some, I think, there's a couple of companies that also have chiming to give Binder some resources. But obviously, Google has maybe more resources.
Yeah.
Also, I should say for the record that Google Colab is maybe like a great tool. It's just been entirely stolen from the Jupyter Thoughts.
Yes.
And
Yes.
it is a bit of a sad story where like a big company takes an open source project and doesn't contribute back, just make it its own for its own purpose and benefit. Anyways, we're using the tool because it's useful, but we are aware of this little story.
Of course. Okay, so about you're not utilizing the GPU, don't worry about that for now, because I think it's just that we were a bit idle for now, but we will use the GPU. So so I guess I do want to move on. So the last time for this pip install command, you have to add a code cell and then include a exclamation point and then include that pip install command. Don't run the conda command. I just included that for, I don't know, people, if they were curious. Don't do that. I should have known not to include it, but that's all right. So anyway, now we move on. We get the data. This is simply just run this cell, shift enter. And so this downloads data for us from DataLad. I don't know if you guys learned about DataLad, but
no, we haven't. The schedule was already quite packed, but
yeah.
If you want to say one word on it, that's fine.
How can I explain
it?
Not.
Let's go. Maybe let's move on.
I'm gonna move on. So this downloaded data, these are MGZ files, and these are the where they exist on the server in this case. So these are all MGZ files. So these are MGH format files. These are our features, and these are our labels. The labels are APARC aseg files. So those are outputs from ReconAll. So the first thing you want to do is understand this data, visualize it, try to understand what it looks like. So we import NumPy. And by the way, to run these cells, you can click on the cell to activate it and then press Shift Enter, or you can press this button here. So we import NumPy, and I included this line here to print the full float values so that you can see what they are, so that it's not scientific notation. Okay, so first, not first anymore, we're well into the notebook. So we read the volume. Nobrainer includes methods to read the volume. This is a very simple wrapper over a package called Nibable, which is very powerful and includes lots of methods for dealing with neuroimaging files. So we read that. What we're doing here is reading in the first row of files the feature volume and the label volume, and now we'll get to explore those. So first, so X and Y are now NumPy arrays. So let's look at the shape of the array. So the shape is 256, 256, 256. So that means that it's a three-dimensional cube in this case. And FreeCipher for some reason likes that shape, 256, 256, 256. And the segmentation volume is the same shape. So that's great because they overlap well. Well, I can't really say that yet, but I mean, their shape is the same, and that's probably a good sign. Oh, someone had file paths is not defined. I think you maybe forgot to run the previous cells. So running these cells, you have to run them in order because some of the variables are defined in previous cells. So, if you're getting undefined errors, go up a few cells and rerun things, because they should run quickly. So, I can do that too. Get data, I'm rerunning that. Understand your data, import NumPy, read the files, get the shape. Okay, and now let's get the minimum and maximum of the features. So here we see that it's 0 and 255. That's because, well, we don't really have to get into that, but that's because of the data type. It's an unsigned 8-bit integer, and those are the bounds. And so FreeServer filled it to the bounds. So for Y, the minimum and maximum are 0 and 2035. So that's great. Now we might wonder, what are the unique values of Y? What are the unique segmentation values? So we can use NumPy's unique function here. And so these are all of the unique values within the label that we loaded. So they go from 0 to 235, as we saw, but it doesn't include all of the values between that. Another thing that you can see is that these are all integers. And that's because these all represent classes. And so FreeServer maps these values to some, like human recognizable name. But we don't have to worry about those names right now. We're just really concerned about having the values, really. So now we want to plot the data so we can visualize it. And we can use Matplotlib for that. Have you guys taught Matplotlib at all?
We had yes, we had some lessons on visualization where some of those tools were introduced briefly. So feel free to it's, to me, it is important that there is some little bit of a repetition so that people can invest deeply. So feel free to repeat whenever you feel is necessary.
Okay, excellent. So Matplotlib is probably the most popular plotting library for Python. So we will import it here. So that should work for everyone. And now we're going to use Matplotlib to plot a histogram. And we'll plot a histogram of the features, that's X here. But the histogram function expects a one-dimensional array. And so we know that our features and labels are both three-dimensional. So we need to flatten it into one dimension. And that's fine for the histogram because we're only concerned about the values and not necessarily their shape. So here we get a histogram. And you can see that the majority of values are close to 0. And that's because most of the brain scan is, well, maybe not most, but a lot of the brain scan is in fact background. The head only takes up so much of the actual scan. So 0 is black, and so the darker bits are closer to 0. Oh, I guess there were 2 calls to this. That's fine. So you can run it again. That's repetition. Now let's plot a histogram of the labels. So this isn't plotting necessarily all of the individual labels and their value counts, but you can see that the vast majority are close-ish to 0. But now we want to inspect what are the actual unique values and how many are there. So we can run this command here. Oops, let me go back up a bit. So I can unpack this command a little bit. We're using the NumPy unique function again on the labels here. And we're telling the unique function that we also wanted to return the counts, the number of times that each unique value appears in the array. So that returns 2 things, the unique values and their counts. And now this is just for visualization. I'm using NumPy's stack function, which stacks arrays. I'm stacking them side by side so that we can visualize easily how many values there are how many times each value appears in the label. So you can see that 0 appears by far, the most. And that's because 0 is background, background. And you can find online free surfer's mapping. It's called free surfer color lookup table, LUT. So you can look through this and see exactly how many times each label appears. So this this tells us a lot, but at least we know that the vast majority is background, and we have a bunch of other classes as well. So now we want to plot these scans so we can actually visualize what the scans look like. So let's expand the plot scan section. Google Colab collapses cells in different sections, so just expand those when you see that. All right, so let's try to plot our features. So Matplotlib includes a matShow function, which you can use to plot a matrix. So let's run that on our features. Okay, so what happened? We got an error, a type error. Invalid shape, 256, 256, 256 for image data. Why did this happen? So it happened because this expects either a 2D array or a 3D array that is like an image. So an image is technically a 3D array where the last dimension has either 3 or 4 channels, RGB or RGB plus opacity or some other color, whatever. In this case, this is not an image that Matplotlib can plot. So we need to plot by slice. So we know that our array is 3 dimensions. So we can index in the first dimension, get slice 120. So that's close to the middle of the brain, not exactly the middle. So let's inspect that shape. All right, so now we have a shape 256 by 256. This is something matShow can work with. So this plotting functionality here might be a bit advanced, but it's still, confusing to me sometimes. So I always need to look up, how do I plot multiple things in the same figure? So don't worry, it does get easier, but I still need help with this stuff sometimes. Anyway, let's run this cell. You'll see what comes up. So we're plotting 3 different slices, and we have 1 row and 3 columns of images. So here, I'm highlighting right now, that is, in the case of this image, the sagittal plane. The first dimension lets you index sagittal plane slices. The second dimension, axial plane or transverse. And the third dimension, coronal. So you need to recognize that this is not always going to be the case. It won't always be that the first dimension is sagittal and the last dimension is coronal. So you really need to visualize your data and see, what is the orientation and which, slices are where and so on. So great, and now we see our brain. It's in the middle. Good contrast. Let's move on. Now we're plotting our, does the fact that, I'm looking at the, so Kendra asked, a while ago, 5 minutes ago, does the fact that the X values go up to 255 have to do with how there's 255 degrees in RGB? It's related, but not exactly. I think RGB also uses unsigned, also uses unsigned 8-bit integers. That's my guess. And the similarity is that this volume also was in unsigned 8-bit integer type. So that's the real reason. But you're right that it is similar to RGB images. Yeah, I think JPEG does that. Maybe PNG, I'm not sure. All right, so let's move on. We're plotting our labels now. So we have, now instead of X, we have Y because those are our labels. And we're indexing sagittal, axial, and coronal. So I'm running that with Shift-Enter. And you can see, some of the labels. So you can see that, they overlap quite well with the brain up top. And so this isn't plotting absolutely all of the labels, but many of them. So let's move on. So, you need to consider what problem you're trying to solve. So in this case, we're trying to make a brain mask. So we have all these different labels, but what we really want is a mask of the brain. So what we can do here is binarize. So what we're saying is collapse all of the labels greater than 0 and make them all 1. So in the end, we're getting a label volume that is all 0s or 1s. 0 corresponds to background, or I should say not brain, and 1 corresponds to brain. So if we do that with this, so Y is a NumPy array. Y greater than 0 is basically performing that operation on every single value. So you get an array full of true or falses with the same shape as Y. And what this is doing is saying wherever Y is greater than 0, set that value to 1. So we run that. And now let's plot the features once again. Aha. So now we see a pretty nice brain mask. There's something going on here with the cerebellum, but we won't worry about that. That's out of the scope of this workshop, I think. I don't know what happened there also. So, okay, great. Let me just look at the chat just to see. Okay, excellent, nothing going on, great. All right, so now let's check the overlap. So we're checking to see whether our brain mask overlaps well with the actual brain in the scan. Because if it doesn't, then our model will learn that, but it's not what we want the model to learn. So as Professor Richards said, you can always overfit your model. The model will try to learn something because it doesn't know what it's seeing. It just is trying to minimize its loss. So any way that it can minimize its loss function, it will do that basically. So we need to be very careful that our features are correct. Oh, sorry, that our labels are correct. So here, the colors are a little bit weird. That's just a quirk that, I could have done this in a more advanced way, but I thought this was fine, so I left it this way. The brain mask is purple. You can see we're plotting with purples, the color map purples, and alpha of 0.2. That's why you get this gray bit on the outside, because it's trying to make the black a little more transparent, but it makes it a bit gray. So anyway, you can see that the brain mask overlaps with the brain quite well. Okay, so, we're looking good. Next, after we have, inspected our data, we want to process it in some way. This is an important step. So there are a few things we're going to do. One is standardize our features. And in this case, what that means is z-score them. So we're going to transform our features, which were originally 0 to 255, and transform them to have a mean of 0 and a standard deviation of 1. There are other things you can do. A typical pre-processing step done with images, like 2D images, is transforming from a range of 0 to 1. Transforming to a range of 0 to 1. So basically you just divide by 255 in most cases, or transforming to a range of -1 to 1.
So Jakub, maybe it's worth explaining why would this step is important, and when would you take it versus not? Is there like a bit of a explanation on why we're doing this?
Yeah. So I'll be honest, JP, I don't know like the theoretical like reason for why. In practice, I've seen that if I don't do this, then the model does not learn well. Another practical reason is that if you train the model, basically it's so that every time you run data through the model, then the input has like a similar, I guess, like feature. It's all within like a similar range or something.
Yep.
So then the model is used to that, basically, so that you train and predict using the same standardization. But I mean, do you know like there must be a theoretical reason. I just don't know it. I'm sorry.
I mean, I can think of one reason, but like it might not be the only one or even the most important one. I think like numerically speaking, if we're starting with like ranges of values that are a little bit misbehaving or very large, so it's possible, it's probable that you want to keep your values as in a kind of a normal range, because that numerically speaking you're going to be better off. But there may be other reasons, and clearly the reapplying the same things on similar things is definitely one of them as well. Yeah.
Okay. Someone asked in the chat, the mean and the standard deviation are calculated on the whole sample or on each individual's? So in this case, it is on the whole sample here. You can do it on individuals. Let's see, is there a more correct way? I'm not sure which one you might want to choose. You'd probably want to choose on like each batch or each individual sample rather than the entire thing, because the model isn't seeing all of the data at once. And when using a pre-trained model, should we standardize the data in the same way as the pre-trained data? Absolutely. If you don't, then your model will most likely not give you the output you're expecting. So you absolutely need to process in the exact same way. So if you're standardizing, so okay, let's move on. So this function basically implements z-scoring. And so we did that. And now let's inspect our mean and standard deviation of this one feature. So this is an important point, I think. You'll see that the mean is some value to the -17th. Sorry, times 10 to the -17th. That's a very small number. It's basically 0. But in a computer, for some reason, you just can't accurately represent, like with 100% accuracy, decimal values. At least not using like the float types. So they're close, but not exactly, those values. The next thing that we need to do is, we have our 3D volume, but with, most GPUs out there, other than, the highest end GPUs, there's not enough memory to train a model on the entire 3D scan. So what we do is separate that scan into blocks, basically. So if we have a 256 scan, 256 on each side, then if we separate it into blocks of 128, non-overlapping blocks, then we get 8 blocks. Does that make sense? Because if you're imagining like the top of the scan, you have 4 blocks, the bottom of the scan, you have 4 blocks. We can separate it into blocks basically. So let's run that. We choose our block shape to be 128 by 128 by 128. And then Nobrainer implements that function to take the full scan, separate into blocks. And later on, we'll put them back together into the full scan. So here we do that. We do the same thing with the labels. Remember that your features have to, your labels have to correspond to your features. So if you're separating the features into blocks, you're going to have to separate the labels into blocks. And each block has to have a correspondence. Meaning that the label block has to correspond to the appropriate feature block. All right, so now we're looking at the shape. You'll see that we made 8 blocks, and they're all 128 by 128 by 128. Same thing for the labels. Let me just take a look at the chat if there are any questions. Yeah, okay. I'm also mindful of the time. It's 11:49 now. So we'll move on, but we'll see if we need to take a break or end or anything.
You'll get another half an hour from 1 to 1:30. Okay. Yeah. So don't worry too much. Yeah. Factor that in.
Okay. Excellent. So that's our shape of our labels and our features. So neural networks expect to have some channel dimension. So we need to add a grayscale channel. And basically, why is X block shape printing 8 by 128 cubed? No, that's a good question. So yeah, it's the number of blocks. Yeah. So just to reiterate what we did with this function here, we're taking our, I'm trying to have to make a cube here. I don't have any cubes around me. No. We have our cube, and then we're separating it out into 8 non-overlapping blocks. And we're doing that because our GPUs don't have enough memory to train on the full volumes. And that's something, we're exploring with other hardware now, because I think it would be important to be able to train on a full volume. So here we're adding a channel dimension. So basically this is adding just 1 dimension to the end. And we can do that to the labels as well to match the shape of the inputs. Okay. And this is fine because we have only 1 class that we're trying to predict, brain or not brain, basically. If you have multiple classes, then that last dimension would be the number of classes that you have. You would have to do what is called one-hot encoding, but I won't get into that now because we won't really be doing that. All right, so this is where we start working with the actual model. So we need to think of an input shape. So what shape does the model expect? So the model will expect, if we're separating it out into blocks, the model will expect that block shape and that channel dimension. In this case, it's 1 because it's grayscale. There will also be a batch dimension, meaning the batch is how many samples the model sees each iteration, but the batch can change, it's variable. So we don't have to include it. So here we run this, we create our input shape, and we see that it's 128, 128, 128 by 1. Okay, so how do you choose your model? There are so many different models out there, even for 3D segmentation. So there's lots of freedom. It's not easy really to create, a new model. I mean, it is easy. It's just a question of how well it will work. So what I do typically is refer to the literature and see what has worked in the past. So one common architecture is for medical image segmentation is the UNet. And for some reason the image isn't coming up. Basically, it uses, it looks like a U. That's why it's called a UNet. So, you have your inputs here, and the way that you put the layers together, it looks like a U. We don't have to get into the specifics of the implementation, but that's where it gets the name. And if you want to look at the implementation, it's within Nobrainer on GitHub. So to instantiate it, I see a good question from David. I see where we added a dimension for a grayscale channel, but how is that populated with information? Maybe I misunderstand how NP expand IMS works. Yeah, so that's a good question. So I hope I explained this well, but because the dimension is only has a size 1, then we're not really adding any information. We're not actually changing the size of the array. It's not like we're adding extra space to the array by adding just a dimension of size 1. So I think this is an important point. So yeah, did you want to say something, JB?
I was going to try to explain that as well. So let's say imagine you have like a set of 3 numbers in an array of dimension 3, because that's 3 numbers. Then you can think of it as the first row or the first column of a 2-dimensional array. So you just now have created a dimension, but you haven't added numbers. You just think of it as the first row or the first column of a higher dimensional array.
Yeah, okay, thank you. Yeah, thank you very much. Okay, so, all right, so let's move on. So in Google Colab, I guess the images aren't working in what's it called? In Binder, I think the images should show up. I think I looked at those and I think they showed up, but who knows? Anyway, let's move on. So let's instantiate our UNet. So you can look at the documentation for this, but the important bits are the number of classes and the input shape. So the number of classes is important because that defines the output shape of the model. So if it's 1 class, you're going to have an output shape of, some 3D thing and then and 1 other dimension of size 1. I hope that makes sense, but it will become clear as we move on. And the input shape is important because that basically is telling the model, what it expects. So we instantiate that. And if Colab is complaining that you're not utilizing the GPU, we will utilize the GPU very soon in the train the model section. So anyway, we instantiated the UNet. So the type of this object is a TensorFlow Keras model. Keras is, it's an API basically. It defines like how you can construct layers, how you can construct models, how you can like define the bits that models are composed of. And so one thing that this model gives you, one of its methods is summary. So you can print the summary, and then you see these are all different layers and the different shapes associated with it. and you'll see that our input shape is here. That is not a 12, that is a 128 that's cut off. I don't know how much you guys have learned about different types of neural network layers, but convolution is, of the typical one that you would use for image processing. That's all I'm going to say about that. Actually, one more thing I will say is the number of trainable parameters. So when you're training your model, you're modifying every step, every time you go through the model to train it, you're modifying all of these parameters. And these parameters are basically what allow you to map your inputs, your features, finally to your labels. And as you get bigger models, you get more parameters. So that's when you need more hardware. What does the concatenate layer do? Concatenate layer, let's say you have some input at the top, and then you do something to it here, and you do something else to it here. You put them back together with concatenate. And I would also highly recommend the TensorFlow documentation. I think it's really well done. They have lots of examples as well. Maybe that's one place where Google shines. Perhaps they stole. Well, I'm not going to throw any accusations out there, but TensorFlow is an open source project, so you can inspect all of their source code and their Keras implementation as well. All right, so the next thing we need to do is choose the optimizer, the loss function, any metrics that we might want to compute while we're training, and other optional things like model saving and things like that. But the main ones are the optimizer, the loss function, and the metrics. So now this is the first time where we have to use TensorFlow, because that's where the implementations of the optimizers are. And the optimizers are basically, the functions that allow the model to actually, how do I say this? Like learn, I guess. Yeah, those are the things that are helping the model to adjust all of those parameters to fit your features to your labels. Or I guess to fit your parameters to your training data, I should say. The loss function is implemented in Nobrainer using TensorFlow, of course. And this is, we'll just use the dice loss. This is a very common loss for segmentation problems. And it's basically a measure of overlap. And we'll also use the dice as a metric. So the dice loss here is, so a perfect dice score is perfect overlap, and that's a score of 1. The loss you want to minimize. So we do 1 minus the dice. So for the loss, a perfect dice is 0. I hope that makes sense. And that's because you want to minimize the loss. The optimizer is trying to minimize the loss value all the time, and it's shifting all the parameters in the model to minimize that loss. So it has to, the better performance, the better your performance, the lower your loss value. But the metric we keep as regular dice, and you should see the difference. This is nobrainer.metrics.dice, and this is nobrainer.losses.dice. All right, so the time is 12:02 now. I guess what we can do, this training can take a little bit of time on Colab because it's 50 epochs. So how about, we let this thing train. It won't take the entire hour, of course, but this might be a good time to break. What do you think?
Yeah, that sounds good. Like we could use the time for the model to train. That sounds like an excellent breaking point.
Yeah.
Uh,
Sorry.
and you'll get more time. You know, in early afternoon, we'll keep Jakub for like half an hour, maybe 40 minutes, for make sure that you finish the tutorial.
Okay, excellent. Let me just run this cell and make sure that it's working, because Danielle ran the cell and got an error. It's after the second epoch. I'm not, oh, got the same error as Danielle. I'm not sure. Me as well, oh no. Me too, okay, everyone. Oh, I ran it without problem. Okay, interesting. So in that case,
it's possible that, sorry, just to jump in, it's possible that you may have missed a cell up a little bit further up when you were splitting the data into blocks. So if that's the case, kind of maybe jump back up to where the data were split into blocks, and just make sure that you've run all of those cells in order before you get here.
Oh no, I get the same thing. Huh. So for some people it works, for some people it does not. Backward data function launch error. One other thing that could, I don't want to delay your lunch, but one other thing that could help is, don't do this. I'm going to try first. So I'm going to restart my runtime. And basically this is clearing everything that was done. I'm going to rerun cells now. So you don't have to install Nobrainer, because that was already installed. I'm just going to rerun all these things and see if that helps. And it should be quick. I got type error. I knew that.
And for those, like if you want to rerun until a certain cell, there's in the menu, in the runtime menu, you have like the run before. So I think that will run, you know, all the cells before a specific cell. So if you sit on one cell and run before, it should rerun everything before that cell. So
hopefully this works.
We'll take a few minutes to see if we can debug things. It seems that for some people it runs, some people it doesn't run. Can I just make sure that this is not those who are using Colab versus those who are using Binder, just to make sure?
Ah, yes.
So if it doesn't run for you, can you tell us if you're using Binder or Colab? Okay, so people are using Colab. Those people have a. I think it might be still. I don't know. I'm not too sure what it is. Sorry.
I'm not sure either, because it works for some people, it doesn't work for others.
Right.
I'm rerunning it now. So yeah, sorry, go ahead.
No, I was thinking like we need to have a bit more of the error messages to debug that.
Yeah. So mine is running right now. Let's see if it errors. It should happen soon if it will. Hopefully not, but we'll see. Oh, Epic. Okay, so it's working for some people, but not all. I don't know why that might be. Oh no, so mine is working now. Okay, so here is my solution. Go into runtime, restart your runtime. So runtime, restart runtime. What this basically does is it clears all of your variables, it clears the memory and so on, and then rerun the cells up until this model fit. Run this model fit cell, and I think that would be a good time to let it go until lunch.
Yeah.
Perfect. Jacob, just before we go, we did have a question that I think maybe would be great to answer just right now, just so that we don't lose it. David had asked, if it turns out that some features relevant to our task or whatever straddles 2 or more blocks, do we prevent our model from incorporating that feature by dividing our volume into blocks?
Sorry, the last part. Can you repeat the last part of that question?
Yeah, so if some of the features in the data are relevant to your task or whatever you're trying to optimize, do we prevent the model from incorporating those features when we divide our volume into blocks? So if the feature is straddling the blocks and we're separating them.
Yeah, no, that's a really good question. So in my opinion, the ideal solution would be able to train on full volumes. As GPU technology gets better, it's more and more possible. But for now, with what we have, I've seen the same thing actually. So especially with the meningioma segmentation, the tumor segmentation model, if a meningioma straddled 2 blocks, then the segmentation wouldn't really be that great along the edges. So this is where augmentation can help. So one thing that I was going to show a little bit later, I think, in this notebook is Nobrainer includes random rigid transformations as augmentation. So basically, imagine this is your brain, or not your brain, but like this is the brain in a brain scan, and you have like some feature that straddles both blocks. Like let's say, I don't know, this gyrus, let's say. The augmentation can be such that you like rotate and I think it's mostly rotate, reflect, and translate the brain in space so that your feature is not always straddling the blocks. So it'll sometimes be only in one block, sometimes it'll straddle, sometimes it'll be upside down or whatever. This can really help the model like, I won't say understand, but actually like create some representation of that feature that's useful. And hopefully then like even if it straddles the block, it will do better. I hope that answered your question. I hope I didn't confuse you.
I think that's good for now. Yeah.
Yeah.
And I think now we should break for lunch if we can. It's 12:10. So Jacob, if you are still around at 1 and you're willing to kind of come back to finish the notebook, that's fantastic.
Yeah, absolutely. Yeah, of course.
Great.
I'll have lunch myself.
Yeah, perfect. And then for those of you who are having issues, we can try and debug over lunch
here and there, and there's some randomness in the training, so you'll get that. But in general, we have a decent loss. We have a decent dice score and a decent loss. So let's try this out on a new scan. So we're using our trained model, and now we're loading a new scan. So this is in the second row of that file path. So of the features and labels. So this is a second participant, different from the first. And this was a question earlier. This is an extremely important point. You need to pre-process your features in the exact same way. So we standardize, we separate into blocks, and we expand the dimensions, basically adding that grayscale channel, which does not actually add data. It's just adding another dimension of 1. Okay, and now we predict. So we're running these test blocks through the model, and we do that with model.predict. And I remember someone during Professor Richard's talk asked, how can I might have, a GPU or great hardware for training. What if I want to predict on, like in real time? Prediction takes much less power and like resources than training. And that's because you're not doing any back propagation, you're not updating any weights, you're just running a forward pass. So this is all just a lot of matrix multiplications, basically. So we predicted, and you'll see that it was 1 second per step. So each block, it took 1 second to predict, approximately, because the total was 9 seconds. So it's a little higher than that. Our shape now is 8 blocks of 128 by 128 by 128 and 1 channel at the end. Do we need to standardize with the same standardized parameters we used in the training set? Standardize, what I mean by that is that basically if you z-scored your data in the beginning, in the training set, you z-score your data in the test set. That's what I'm saying here. So that the distribution is always, its mean 0 and standard deviation of 1. It's not really a normal distribution, but that seems to be okay. So the outputs are probabilities. So the model will, but you don't use the standard deviation from the training set. Maybe we can talk offline about that. Or perhaps someone else can help. So the outputs are probabilities. They are in the range from 0 to 1. And so we can apply a threshold. It doesn't have to be 50%. In the literature I've seen, it can be 30%. You can make it whatever you want, honestly. Whatever seems to work, I guess. So here we'll apply a threshold of 50%. So if it's greater than 50%, we call that brain, and otherwise it will be not brain or background. So we can do that here. This will create a Boolean array, so all the values are true or false. And now we've removed that last dimension with squeeze. So squeeze will trim, dimensions that are 1. So that you no longer have those dimensions, and you'll see that now our shape is 8 by 128 by 128 by 128. So these are blocks. So what we want to do is recombine those blocks into a full scan. So Nobrainer implements this, and our expected output shape is 256 by 256 by 256. So we run this, and now our brain mask is that shape. And we can plot it, and we'll plot it against the input volume. So this is the volume we gave, and this is the output. So, I mean, it does look like a brain. It's not great, but it definitely does look like a brain. So, even from that one scan, we have a model. This is not a model, that I would ever use really for anything other than like debugging, but it works, meaning that it gives output. And let's look at the dice score. So we can use the Nobrainer metrics module, and it implements dice. So let's run that. And the dice score is 0.87, where 1 would be perfect overlap. So, actually not that bad. The caveat to all this is that that model, just please remember that it was only trained on a single scan. So it's not going to actually generalize all that well. All right, excellent. So what have we learned so far? We've learned how to, understand your data, how to visualize your features and your labels. We also learned that training is slow. In addition, we learned that training can be ridden with errors. So this is common, in software development and I guess scientific computing in general. it's always an iterative process where you run into errors, you figure it out, and then you move on. So please don't get discouraged by that, because it happens to everyone. Also, the models do not generalize well. So recommendation, and I believe Professor Richards recommended this. If possible, begin with a model that was trained on lots of data. I think exactly what he recommended was find lots of data that you can pre-train your model on. But in this case, we have a pre-trained model. This is, what we're going to do here is download the Nobrainer model for brain extraction, which is a unit that was trained on blocks of 128 cubed. All right, so now we're going to, I guess, reload that same path that we evaluated on. Z-scored, and then, did that work? Yes, okay. And now separate into blocks, expand DIMS to add the grayscale channel. And now what we do is predict using the pre-trained model. So you can see, here we downloaded this file. It comes from GitHub. I uploaded it there. We name it with this name. It's an HDF5 file. And then we load it here with TensorFlow. Okay, so now with our inputs, we can predict. And this is something that you can do on CPU as well. So on, on an i7 or something like that, this might take, a minute or a few minutes at most. All right, so that's done, 1 second per step. And now we do the same thing where we threshold. Here I choose 50% or 0.5, squeeze the last dimension, and then reconstruct the full volume. Okay, that happens very quickly. And now we plot it. All right, and this is, a much higher quality brain mask now. And you'll notice that, these scans were not part of the training set. And yet it's doing quite well on these scans to create the brain mask. So I think a takeaway from here is that transfer learning, or like starting with a pre-trained model, can be very powerful, especially if you don't have lots of data. And this is also important if the model you're starting from was trained on similar data. All right, so let's assess our dice score, assess our performance. And what do you know? It's 0.956, much higher than the 87 or 88 we got earlier. And also we get much more of the finer details, which is great. And we didn't have to do any training. All right, I wanted to, so it's 1:17. I think I'll skip this part now because this is basically doing the same thing. This is now downloading the Bayesian model, the variational model, and predicting on that. So, for those that want to, you can run these cells another time, but in the interest of time, I would like to move on. Especially because it basically teaches the same lessons that we just got through, how to train with a pre-trained model. Oh, sorry, how to predict with a pre-trained model. All right, so now we're at this part here. So we learned a lot, and that's great. We learned how to process our data, instantiate a deep neural network architecture, train our model, and predict. We even learned how to use a pre-trained model. And this works really well for learning the basics and debugging and predicting on a few scans. But importantly, it does not scale. So if you're training on any respectable amount of data, you will not be able to fit it into memory. Also, performing augmentation during training can be important, but it's not really clear how we would do that with what we've learned so far. And another thing, we don't want to load and then process and then train. We would much rather load, process, and train in an interleaved fashion so that our GPU and CPU are never idle. In other words, so that our GPU is never like starved for data, so that it's never waiting for data to come in. And that's especially important if you're using paid cloud services. All right, so here's a sort of more detailed workflow of what would happen in the real world. And this is definitely the workflow that I follow. So about 11 minutes left. And I guess I would like to leave some time for questions in the end. So I won't read through all of this, but sorry, go ahead.
I was going to say, like, if you end at 30, I'm sure like a guy will give you a couple of more minutes for questions.
Okay. The main parts of this workflow are first to prepare your data on disk. So you need to have access to lots of data, and you want to have a mapping between features and labels. So these are paths to corresponding MRI files in this case. And you want to separate all of your data into 3 sets, ideally. You want to have a training set on which you train. You want to have a validation set on which you can validate your model as you're training it. And finally, you want to have a testing set where after training is done, you can predict on completely unseen data, and you can see how well your model does there. And it's important that your testing set is not seen during training, because during training, you're sort of iteratively improving things, improving hyperparameters, and you want to leave your testing set out of that process. Third point related to preparing data, TensorFlow has a preferred file format for data, and it's called TF record. And that's the preferred file format for data that does not fit into memory. So, you could use NumPy arrays, but, even if you have like, 100 scans or something, typically you won't be able to fit that onto your RAM. And this format is also great because it allows for parallel reading. So you can read from multiple files at once. All right, so I think we got through the processing pipeline. We sort of talked about that before. Choosing a loss function, choosing a model, yes. You can also create the model yourself with the TF-Keras API and then use, any of the Nobrainer functionality. Finally, training and evaluating. Okay, so this is what a mapping between features and labels might look like. You have a CSV, a spreadsheet, and each row is a pair of features and labels. And the number of rows that you have would be the number of scans that you have. Okay. So let's do that here. We'll get that same data. We'll read that CSV, which is the mapping. And then we separate into training, validation, and testing. And here I'm just using simple indexing, but in the real world, you would want to shuffle around and separate after some, you randomly shuffle, so that you distribute like different sort of features among all 3 sets. All right, the next step is verifying that all of these volumes have the same shape and that all the labels are integer-ish. So if they're floats, that they can be converted safely to an integer. So we do that because, this is, I guess, a bit of quality control. You don't want volumes that are different shapes because then you can't stack them. Okay. And now we convert the volumes to TF records. And TF records is a format that would be on disk that, like, we're copying the data from the MRI into TF records, and then TensorFlow can very quickly read that data and process it. So Nobrainer includes functionality for this. The TF record format initially can be a little bit, I don't know, I might say not daunting, but a little bit confusing. It uses protocol buffers, or like a protocol buffer sort of format, I believe. So in any case, Nobrainer makes it quite easy. So we take our training paths and we take all of those and save them to files with this name. And does Nobrainer read, write, make files? So Nobrainer uses Nibable for all of its neuroimaging I/O. So if Nibable can read it, then Nobrainer can read it. So I think Nibable can read, make files. So in that case, yes, but it depends on Nibable in that case. Okay, apparently there are bugs. Okay, that might be good for Nibable, an issue or a pull request better. Okay, I won't go through the details here in the interest of time, but here we're saving our data to TF record. And this is also useful because, so, you know, apparently the issues with different neuroimaging file formats and different readers. Once you convert it to TF record, you can share these very freely, and you can, you know, upload them to HPC or something like a cloud provider, and then run it there without having to worry about I/O, because TensorFlow is guaranteed to be able to read these things. All right, so the saving is pretty much done. And we saved 3 files for the training path because we're creating different shards. So we split our different sets into different files so that when we end up reading them, we can read them in parallel, and that speeds things up. It also makes the conversion process faster. And you'll see that if you list the contents of the directory, you'll see different files. All right. So this is, I think, also a point where Nobrainer shines. You can create an input processing workflow very easily. So there are a few parameters that you'll need to think about: the number of classes, the batch size, which is the number of samples that a model sees at each step. So in this case, batch size of 2 would mean you're seeing 2 of those blocks, 2 blocks per training step. The shape of the original volume, the shape of blocks that we want to separate into. Augmentation, here it's pretty straightforward. It just means if we want to apply random rigid transformations. So rotation, translation, reflection. The number of epochs, meaning the number of times we iterate over the entire data set. Shuffling. Shuffling is very important, by the way. If you don't shuffle, your model might learn the something about like the order of input data. So you absolutely need to shuffle your training set, that is. And then number of parallel calls, and TensorFlow allows you to, TensorFlow can sort of figure that out, the number of CPUs to use for things. All right, so this function, lots of parameters that we all set up here. This is implemented in the, I didn't run this, I'm sorry. So I run that, and then we run this. So this is creating a TensorFlow data set now that loads data, separates it into blocks, creates the correct batch size, applies augmentation if we wanted to, shuffles it, and basically prepares it for training. And at that point, it's ready for training. So this is our validation data set. You'll notice that we don't shuffle the validation set. And that's our test set. And notice again, we don't shuffle the test set. Oh, and it knows where to get the data from because we gave it a certain file pattern. And that's like a glob pattern, basically. Next, we want to choose our loss function. We choose a model. Like I said, many different options. Here, we're just going to load that same brain extraction model, that we used earlier. We're running out of time, but that's okay because we're almost at the very end. So this is actually working out perfectly. So for transfer learning, this might be a bit advanced, but the pre-trained model has already learned a lot about the features of its own training data. So when you're training this, you want to apply, typically you want to apply some sort of regularization, and you want to apply, like I said, typically a relatively low learning rate. And this is something I do so that you don't drastically shift the weights that the model has already learned. It's more like you're sort of fine tuning it to your problem. So you don't want to like drastically change the weights as if you were training from scratch. You want to more fine tune it. So that is done here. And now we can train. And here we train. It's going to train for 5 epochs, and each epoch is 28 steps. And this is the algebra that you might do to figure out the number of steps. You actually don't need to know the number of steps offhand, because during the first epoch, the model will go through and cache, I guess, the number of steps that it took in the first epoch. So that actually will happen for a little bit. So I'm just going to train this for 1 epoch. That'll be 28 steps. Then we will evaluate it, and that will be it for me, and I can answer questions. I see one question: how many epochs do people typically run during training? It varies. So that brain extraction model was only trained for 5 epochs, but those 5 epochs took, how long did that take to train? Those 5 epochs took more than 5 days to train, I believe. And that's due to, it takes time because the data are large and they're 3-dimensional. On what data size? That was 10,000 brain scans. So 10,000 samples separated into 8 non-overlapping blocks, so 80,000 blocks in that case. One thing that I did not demonstrate in this notebook, but if you have access to multiple GPUs, so for example, on HPC, you can train with multiple GPUs, and you can look at the TensorFlow documentation on how to do that. Another pretty basic question, probably not so basic, don't worry. This model does not examine the spatial relationships of voxels in relation to each other, right? Is there a way to add that as a feature? Great question. So that's an area of research that I'm personally very interested in. How to explain what these models are doing. How do we improve, our own understanding of these models? Because at the moment they're more or less black boxes. So, but to answer your question, yes, it does examine the spatial relationships of voxels, and that's done through the convolutional layers. So it has it understands the spatial relationships of fairly local, voxels in a fairly local region. But typically I have not seen people separate out those features manually. I would expect the model to learn those things on its own.
So we are going to let that run, Jakub.
Yeah.
Is there any other questions? I think I saw a epoch versus a batch clarification somewhere, but.
Oh, okay. Yeah, that's a great point. So let me start by saying that sample is one instance. So a sample in our case here would be 1 block, 1 subblock from the volume. So you have 8 samples per volume. So you have one, that's a sample. A batch is how many samples you're feeding to the network at one time. And then an epoch is one pass through your entire data set. So after you go through your entire data set once, that's an epic.
Thank you for the clarification. So are there any other questions while we're waiting for?
Yeah, this should be done in a few seconds. There was one question, do you think that would be a useful thing to try or too computationally expensive? You know, if you want to try it, by all means, go right ahead. It might work, it might not, but I think the best way to know is to actually try it. It might be computationally expensive, but I don't think that's a reason to stop, because you know, you might find that it's not computationally expensive. I hope that answers it. All right, so this is done. Just about. All I wanted to show was the training, the output, like the history basically from training, and then evaluate. And I wanted to show you guys that basically transfer learned model can work in many cases. So here is, oh, that's weird. Oh, because there's only one epic, that's why. Okay, so sorry, because before I had a training for 5 epics, but that would take too long. Anyway, here we'll evaluate, and you'll see that the dice is quite good. So yeah, it's 9538 or 9437. Yeah.
Jakub, that was excellent. Thanks so much indeed. We're really, really grateful, and it's a really fun and interesting work that you've done. And also, I would like to re-emphasize that you know, all the work that has been done to make that available for us and for everyone is really awesome. So congrats, thanks again. We really appreciate, and I don't know if you're going to stay online for the rest of the afternoon or not. Probably not, but if you do, I'm sure there will be other questions if you are. If not,
okay.
no, sometimes you know, we can forward your questions.
Absolutely, yeah, or connect on GitHub or Gmail or anything. Yeah, thank you very much, everyone. Thank you so much.
Thank you.